let me tell you something extraordinary. It's been there all along, not hidden behind the sun, not lost in the vastness of space, not some distant, invisible world beyond our reach, but right there visible to the naked eye, glowing steadily in the sky. Venus has always been one of the most prominent objects humans could observe long before telescopes, long before science as we know it. If you step outside just before sunrise or just after sunset, you can still see it. A brilliant point of light, brighter than any star. It doesn't twinkle like the others. It shines with a steady, almost unnatural clarity as if it's trying to get your attention. And for thousands of years, it did. Ancient civilizations didn't see Venus as just another light in the sky. They gave it meaning. They gave it identity. To them, it wasn't a planet, it was a presence, a symbol, a force. The Babylonians called it Ishtar, a goddess of love and war. The Greeks associated it with Aphrodite. The Romans followed with Venus. Across cultures and continents, this single point of light became one of the most important celestial objects in human history. They tracked it carefully, not just casually observed, but recorded its movements with precision. They noticed something strange. Sometimes it appeared in the morning sky, rising before the sun. Other times it appeared in the evening, setting after the sun. For a long time, people thought these were two different objects, the morning star and the evening star. But they weren't. They were the same world. Even without modern tools, ancient astronomers were already uncovering patterns, already trying to understand the deeper structure of the cosmos. Venus wasn't just beautiful, it was mysterious, and that mystery only deepened with time. When telescopes were finally invented, astronomers turned them toward Venus, expecting answers. Instead, they found more questions. Through a telescope, Venus doesn't look like a star at all. It shows phases like the moon, sometimes a crescent, sometimes nearly full. This was one of the key observations that helped confirm that planets orbit the sun, not the Earth. But even with this breakthrough, Venus refused to reveal its true nature, because no matter how powerful the telescope became, its surface remained hidden, completely obscured by thick reflective clouds. For centuries, no one could see west. Hat lay beneath, and in that absence of information, imagination took over. Some scientists speculated that Venus might be a tropical paradiso world covered in oceans, rich with vegetation, perhaps even teeming with life. After all, it was similar in size to Earth, similar in mass, located not too far away. It felt like it could be Earth's twin. But then came the space age. When humanity finally sent spacecraft to study Venus up close, the illusion shattered. The truth was not just different, it was extreme. The first probes revealed a planet with surface temperatures around 465 degrees Celsius hot, enough to melt lead. The atmospheric pressure was about 92 times that of Earth, equivalent to being nearly a kilometer underwater. The skies were filled with thick clouds of sulfuric acid. This wasn't a paradise. It was a pressure cooker, a planetary scale inferno. Suddenly, Venus transformed in our minds from a hopeful twin to a cautionary tale. Scientists began to understand that this hellish environment was caused by a runaway greenhouse effect. Carbon dioxide trapped heat in the atmosphere, raising temperatures. Higher temperatures released more gases, trapping even more heat, a feedback, AK loop with no escape. Venus became the ultimate warning, a demonstration of what could happen when atmospheric warming goes too far. It was no longer just a planet, it was a lesson, a glimpse into a possible future for Earth. And for decades, that's where the story seemed to end. Venus was studied, yes, but mostly as an example of failure, a world where everything went wrong, a place fundamentally different from Earth despite its similarities. But here's the problem. That interpretation assumed that Venus had always been this way, that it was always destined to become a hellish world, that from the beginning it followed a path completely separate from Earth, and that assumption may be completely wrong. Because what if Venus didn't start out as a disaster? What if it wasn't always a warning? What if, for most of its history, Venus was something else entirely, something far more familiar, something that challenges everything we thought we knew? The brightest object in our night sky might not just be a symbol of destruction. It might be the remains of a world that once looked a lot like home, because the Venus we see today is not the Venus that always existed. For a long time, we treated Venus as an outlier, a strange, hostile world that simply turned out differently from Earth. But when you look closely at the data, that assumption starts to fall apart. In fact, Venus and Earth are almost eerily similar. Start with size. Earth's radius is about 6,371 kilometers. Venus, roughly 6,052 kilometers, less than a 5% difference. On a cosmic scale, that's nearly identical. If you place them side by side, they would look like twins. Then there's mass. Venus is about 81.5% the mass of Earth. That means its gravity is only slightly weaker. A human standing on Venus, ignoring the extreme conditions, would feel almost the same weight as they do on Earth. The similarity matters more than it seems. Mass and size determine how a planet evolves. They influence how much atmosphere it can hold, how much internal heat it retains, and how long geological activity can continue. Smaller planets like Mars cooled quickly and lost much of their atmosphere, but Venus, like Earth, had the capacity to remain geologically active for billions of years. Then there's composition. Both planets are made from nearly the same ingredients: iron, silicon, magnesium, oxygen, N. Their densities are remarkably close, suggesting similar internal structures: a metallic core, a rocky mantle, and a solid crust. They didn't just end up similar by coincidence. They formed from the same region of the early solar system, around 4.5 to 4.6 billion years ago, from the same protoplanetary disk. The same cloud of gas and dust that gave rise to Earth also gave rise to Venus. They are quite literally planetary siblings, and that means something important. They likely started with the same basic conditions, the same building blocks of atmospheres, the same initial supply of volatile compounds: water, carbon dioxide, nitrogen. During the early history of the solar system, both planets were bombarded by comets and carbon-rich asteroids. These impacts delivered water and organic molecules, the essential ingredients for oceans and potentially life. There's no reason to believe Earth received something special that Venus didn't. If Earth got oceans, Venus should have gotten them too. And this is where the story begins to shift. Because for decades, the idea that Venus once had water seemed speculative, almost wishful thinking. But modern measurements tell a different story. The key evidence lies in the atmosphere. Today, Venus is extremely dry. Its atmosphere contains only trace amounts of water vapor. At first glance, it looks like a planet that never had much water to begin with. But the chemistry tells us otherwise. Specifically, scientists measure something called the deuterium to hydrogen ratio, often written as D/H. Deuterium is a heavier form of hydrogen. When water is lost from a planet's atmosphere, the lighter hydrogen escapes into space more easily, leaving behind a higher concentration of deuterium. So, if a planet has a high D/H ratio, it means it has lost a lot of water over time. And on Venus, that ratio is extreme, about 150 times higher than Earth's oceans. That's not a small difference. It's a massive signalochemical fingerprint that points to a dramatic past. It tells us that Venus didn't just lose a little water. It lost an enormous amount. Enough that, if you work backward, the planet may once have had significant bodies of water, possibly even oceans, covering large portions of its surface. Some models suggest shallow seas. Others suggest something more dramatic: global oceans kilometers deep. There's still uncertainty about the exact amount, but the direction is clear. Venus was not always dry. It was once a water-bearing world. And if you combine that with everything else, the similar size, the similar mass, the similar composition, the shared origin, you arrive at a striking conclusion. Early Venus may have looked a lot like Earth, not identical, not a perfect mirror, but close enough that under the right conditions, it could have supported a stable climate, liquid water, and the kind of chemistry that leads to life. This is where the idea of Earth's twin becomes more than just a phrase. It becomes a real possibility. Because if two planets start almost the same, receive the same materials, and evolve under similar physical laws, then their early histories might not be so different after all. Which raises a deeper question. If Venus had everything Earth had in the beginning, why didn't it end up the same way? Why did one planet stabilize into a life-supporting world while the other spiraled into a runaway greenhouse? The answer isn't simple. It's not about a single difference. It's about a chain of events of divergence that may have started small, almost inside, significant, and then amplified over time. A slight variation in distance from the sun, a difference in rotation, a change in atmospheric balance, tiny factors that over billions of years reshaped an entire world. And that's what makes Venus so important, because it's not just a failed planet, it's a controlled experiment. Two nearly identical worlds, two different outcomes, and somewhere in that divergence lies the answer to one of the most important questions in science. What makes a planet habitable and what destroys that habitability? Venus isn't just a mystery, it's a mirror, not showing us what Earth is, but what it could have been. If Venus once had water, the next question becomes unavoidable. How long did it last? Was it a brief phase, an early short-lived ocean that quickly vanished under the sun's heat? Or was it something far more stable, something that endured? For a long time, many scientists assumed the answer was simple. Venus is closer to the sun than Earth, so it must have always been too hot for liquid water. End of story. But that assumption turned out to be too simplistic, because planets are not defined by distance alone. They are defined by systems, atmospheres, rotation, clouds, chemistry. And when scientists began to model those systems more accurately, the results were unexpected. In 2016, a team of researchers at NASA Goddard Institute for Space Studies ran detailed climate simulations of early Venus. They weren't guessing. They used the same advanced climate models that are used to study Earth's future, adapted to Venus's conditions. They tested different scenarios, different atmospheres, different solar intensities, different rotation speeds. And what they found surprised the entire planetary science community. Under realistic early conditions, Venus could have maintained stable surface temperatures between roughly 20 degrees Celsius and 50 degrees Celsius, not just for a short time, but for billions of years. That changes everything, because those temperatures are not just tolerable, they are ideal for liquid water, ideal for stable oceans, ideal for complex chemistry. In other words, early Venus may have been not just habitable, but comfortable. So how is that possible? How can a planet closer to the sun avoid overheating? The answer lies in something deceptively simple: clouds. But not just any clouds planet-wide, highly reflective cloud systems driven by Venus's unusual rotation. Venus rotates extremely slowly. One full rotation takes about 243 Earth days, and it spins in the opposite direction compared to most planets. This slow rotation creates a very different kind of climate system. On a fast-rotating planet like Earth, the sun rises and sets quickly. Heat is distributed relatively evenly, and weather systems move continuously. But on a slow-rotating planet like Venus, one side of the planet faces the sun for an incredibly long time. At first glance, that sounds like a disaster constant heating, no relief. But the atmosphere responds in a very specific way. Instead of overheating, the sunlit side develops thick, persistent cloud cover. These clouds act like a giant mirror, reflecting a huge portion of incoming solar radiation back into space. This effect is called high albedo. And on early Venus, it may have been strong enough to offset the increased solar energy from being closer to the sun. In simple terms, the more sunlight Venus received, the more it reflected away. A natural cooling system, a built-in stabilizer. This cloud feedback mechanism is one of the most important discoveries in modern planetary science, because it shows that habitability is not just about position, it's about behavior. It's about how a planet responds to energy. And in the case of early Venus, the response may have been remarkably effective. The simulations suggest that oceans could have remained stable for 2 to 3 billion years. To understand how long that is, consider this. Complex life on Earth only began to emerge around 600 million years ago. That means Venus may have been habitable for a period 5 times longer than it took for complex life to evolve here. That's not a narrow window. That's an era, an entire planetary chapter where rivers could have flowed, clouds could have formed, and chemistry could have unfolded in ways very similar to Earth. And where there is stable water, energy, and time, there is always the possibility of life. Now, this doesn't mean Venus definitely had life, but it does mean something important. If life can arise under the right conditions, Venus had those conditions for a very long time, which forces us to rethink something fundamental. The idea of the habitable zone. Traditionally, scientists define a narrow band, around a star where liquid water can exist on a planet's surface. Too close and water evaporates. Too far and it freezes. By that definition, Venus sits just inside the inner edge, too close to the sun to be habitable. But early Venus challenges that idea, because despite being closer, it may have maintained habitable conditions anyway. Not because the definition is wrong, but because it's incomplete. The habitable zone is not a fixed boundary. It's dynamic. It depends on atmosphere, cloud behavior, rotation, and planetary feedback systems. In other words, two planets at nearly the same distance from a star can have completely different outcomes, and Venus proves it. It tells us that habitability is not just about where a planet is, but how it works. And that realization has implications far beyond our solar system. Because if Venus could stay habitable for billions of years under the right conditions, then many exoplanets we once dismissed might also be capable of supporting life. Worlds closer to their stars, worlds we thought were too hot, worlds we overlooked. Venus is not just rewriting its own history, it's expanding the possibilities of life in the URS. But that only makes the next question more urgent. If Venus had everything it needed to remain habitable for billions of years, what caused it to lose all of it? If Venus had oceans, if it had a stable climate, if it remained habitable for billions of years, then something profound must have happened. Because the world we see today, Venus, as a superheated, high-pressure inferno is not a gentle continuation of that past. It is a transformation, and not a slow one. The evidence points towards something far more dramatic, a planetary scale catastrophe. To understand this, scientists turn to one of the most reliable records a planet can offer its surface. Unlike Earth, where plate tectonics constantly reshapes the crust, Venus preserves a different kind of geological history. There are no moving plates recycling the surface, no oceans erasing ancient terrain. Instead, the surface acts like a record one that can be read through impact craters. Over time, planets accumulate craters from asteroid impacts. The longer a surface remains unchanged, the more craters it gathers. Older regions become heavily scarred, while younger surfaces appear smoother. When scientists mapped Venus's surface using radar data, they expected to see a mix some very old regions, some younger ones like we see on Earth or Mars. But that's not what they found. Instead, they saw something strange. The crater distribution across Venus is almost uniform, not heavily cratered, not completely smooth, but consistent everywhere. And that consistency reveals something extraordinary. The entire surface of Venus appears to be roughly the same age, about 700 to 800 million years old. That shouldn't be possible under normal conditions. On Earth, different regions have different ages because the surface is constantly being recycled. On Mars, some areas are billions of years old, while others are much younger. But Venus shows no such variation, which leads to one conclusion. At some point in its history, the entire surface was reset, wiped clean, resurfaced. This is where the leading hypothesis emerges. Sometime between 700 million and 1 billion years ago, Venus may have experienced a global volcanic resurfacing event, a period of extreme geological activity so intense that it covered most, if not all, of the planet in fresh lava. Not a single eruption, not even 1,000, but a sustained planet. Wide outpouring of magma. Imagine vast regions of the surface cracking open, releasing enormous quantities of molten rock. Lava flooding across continents, burying older terrain under kilometers of new material. A world being remade from below. But the surface wasn't the only thing affected, because with that lava came gases, enormous amounts of gases. Volcanoes don't just release molten rock, they release carbon dioxide, sulfur compounds, and water vapor. On Earth, these gases are part of a balanced cycle. Carbon dioxide is absorbed by oceans and locked into rocks through chemical weathering. But on Venus, that balance may have failed. If this volcanic event released enough carbon dioxide into the atmosphere, it could have triggered a runaway greenhouse effect on an unprecedented scale. The process feeds on itself. More carbon dioxide traps more heat. More heat causes oceans to evaporate. Water vapor, and even stronger greenhouse gas, adds to the warming. Temperatures rise further. More gases are released, and the cycle accelerates. At a certain point, it becomes unstoppable. The oceans, if they still existed, would begin to boil away. Not gradually, but irreversibly, as water vapor film led the atmosphere. Sunlight in the upper layers would break those molecules apart. Hydrogen, the lightest element, would escape into space. Oxygen would remain reacting with surface rocks, becoming locked away. And over time, the planet would lose its water completely. What remains is what we see today: a dense carbon dioxide atmosphere. Surface temperatures around 465 degrees Celsius, crushing pressure. A world where liquid water cannot exist. A world that cannot easily recover. If this scenario is correct, then Venus did not slowly drift into its current state. It crossed a threshold, a tipping point, and once it did, there was no going back. What makes this even more striking is the timing. This transformation may have occurred relatively recently in geological terms within the last 20% of the solar system's history. That means for most of its existence, Venus could have been stable, habitable, even Earth-like. And then in a comparatively short span of time, everything changed. A 3 billion year chapter of potential habitability ended by a catastrophic shift. This is why Venus matters so much, because it shows that planetary habitability is not permanent. It's fragile. It can last for Billy on some years and still be lost, not necessarily through slow decline, but through sudden, overwhelming change. Venus is not just an example of a planet that failed. It's an example of a planet that worked for a very long time until something pushed it beyond its limits. And that raises a question that is impossible to ignore. If a world so similar to Earth could transform so completely, what does that say about the stability of habitable planets in general? And more importantly, what does it say about our own? Even after everything we've uncovered ancient oceans, a stable climate, a catastrophic transformation, Venus still holds one of the most unsettling possibilities of all. What if its story didn't end? What if something survived? In September 2020, a team of scientists led by Jane Greaves announced a discovery that immediately shook the scientific community. They had detected a gas in Venus's atmosphere, phosphine. On its own, phosphine, pH 3, is just a simple molecule 1 phosphorus atom bonded to 3 hydrogen atoms. But in planetary science, context is everything. And in the context of Venus, phosphine shouldn't be there, because Venus's atmosphere is extremely hostile to T. Hat molecule. It's highly oxidizing, filled with sulfuric acid droplets and reactive chemicals that should destroy phosphine quickly. Under those conditions, phosphine cannot easily accumulate, which means if it's present, something must be producing it continuously. On Earth, phosphine is associated almost exclusively with biological processes. It's produced by certain anaerobic microorganisms, life forms that thrive in environments without oxygen. There are some non-biological ways to produce phosphine: lightning, volcanic activity, high-pressure chemistry, but none of them, based on current models, seem capable of generating it in the quantities initially reported on Venus. That's what made the discovery so explosive. Not because it proved life exists there, but because it introduced a serious anomaly, a gap in our understanding. However, science doesn't move on excitement alone. It moves on verification. And almost immediately, other research teams began reanalyzing the data. They confirmed that a signal was present in the spectrum of Venus's atmosphere, but the interpretation became a subject of intense debate. Some studies suggested the original estimate around 20 parts per billion was too high, possibly due to calibration issues. Revised estimates brought it down to between 1 and 5 parts per billion. Still significant, still difficult to explain, but less dramatic. Others proposed that the signal might not be phosphine at all. It could be sulfur dioxide, a far more common gas on Venus appearing at a different wavelength under specific conditions. So where does that leave us? In a place that science rarely admits, but often inhabits. uncertainty. The signal is real, but its identity is still contested. And even if it is phosphine, its origin remains unknown. It could be chemistry we don't yet understand, or something we haven't considered at all. But here's why this matters beyond the debate itself. It has refocused attention on a specific region of Venus that had long been overlooked its clouds. Because while the surface of Venus is unimaginably hostile, its upper atmosphere tells a different story. At altitudes of about 50 to 60 kilometers, conditions become surprisingly moderate. Temperatures range roughly between 0 degrees Celsius and 60 degrees Celsius. Pressure is similar to what we experience on Earth. It's not comfortable, but it's not impossible. In fact, it's the only region on Venus where life as we currently understand it could potentially exist. Of course, there are still major challenges. The clouds are composed largely of sulfuric acid. Ultraviolet radiation is intense. Nutrients are scarce. But extremophiles on Earth organisms that thrive in extreme environments have already shown us that life can adapt to conditions once thought uninhabitable. Acidic lakes, deep-sea hydrothermal vents, high radiation environments. Life, when it emerges, has a tendency to persist. So imagine this. If Venus once had oceans, if life had time billions of years to emerge, and if the surface gradually became uninhabitable, where would that life go? The answer, at least in theory, is upward, into the clouds. As surface temperatures rose past the boiling point of water, past 100 degrees Celsius, 200 degrees Celsius, 300 degrees Celsius, any surviving organisms would be forced to adapt or disappear. The upper atmosphere, with its relatively mild conditions, would become a refuge, a last habitable zone on a dying world. This idea is speculative, but it is scientifically grounded, and it is testable. That's why, after decades of neglect, Venus is once again becoming a priority for exploration. New missions are being designed to answer these exact questions. NASA Da Vinci mission will send a descent probe through the atmosphere of Venus, directly sampling its chemical composition as it falls toward the surface. It will measure noble gases, isotopic ratios, and atmospheric structure with unprecedented precision. Another mission, Veritas, will map the planet's surface in high resolution, searching for geological evidence of past water minerals that can only form in the presence of liquid water. Meanwhile, the European Space Agency is preparing the Envision mission, which will study both the surface and atmosphere, aiming to understand how Venus evolved over time. Together, these missions represent something more than scientific curiosity. They represent a return, a recognition that Venus is not just a failed planet, but a key to understanding planetary evolution itself, because Venus forces us to confront a profound possibility. That habitable worlds can exist for billions of years and still be lost. That life, if it arises, may not always endure, and that even the most Earth-like planets can follow radically different paths. But it also opens another possibility, one that is harder to ignite, or that somewhere in the thick reflective clouds of Venus, there may still be chemistry we don't understand, processes we haven't discovered, or perhaps something alive, not on the surface, not as we imagine it, but suspended in the sky of a world that once had oceans, a world that may have had its own biological history, a second experiment in life unfolding just 40 million kilometers away, hidden not in darkness, but in brightness, right there in our sky, waiting to be understood.